Finally, I want to quickly discuss how this can be generalized to mixture models of different, using different distributions besides multivariate Gaussians. So we've actually already discussed everything necessary to give an outline of the algorithm for doing maximum likelihood EM for any generic mixture model, and it looks like this. So now we have data x1 through xn, where we assume each data is in some space, and this space can be anything. It can be quite complicated if we want. It doesn't have to be RD. And our goal now is to maximize the log of the likelihood of the data. And because we again make an IID assumption, it's the sum of the log of the likelihoods of each observation, given the mixing weights pi, so this does not change at all, and also given some parameter set theta, where we're going to be generic here. And this cluster-specific likelihood of x given the kth cluster is going to be generic. With the Gaussian mixture model, this was a multivariate Gaussian, and theta k was the kth mean and the kth covariance for that Gaussian. Now this is any probability distribution, and theta k is a set of parameters for that distribution. The EM algorithm in this case looks like the following. For each iteration, we have the E step. This is identical to before, where we say for each observation I, we calculate the conditional posterior probability of the ith observation coming from the kth cluster. That's equal to the prior probability of a point coming from the kth cluster times the likelihood of the ith data point coming from the kth cluster, where we use the parameter for the kth cluster to evaluate this likelihood. This is now different from before. Before this was a multivariate Gaussian. Now it's whatever distribution that we've defined on xi according to the problem that we're looking at. So we calculate this, and then we normalize to get a distribution, and that's the conditional posterior probability of the ith point coming from the kth cluster. The M step then is similar to before, in the sense that for the kth cluster, we now sum the probabilities of all of the data coming from that cluster. So we get the expected total number of points we're going to see from that cluster, and then we update the prior probability of any point coming from the kth cluster as taking that sum nk and dividing by the total number of points. So this is no different from before. It's the same exact thing. This now has to remain generic. So when we want to update the parameter to the distribution for the kth cluster, what we have now is this problem, where we want to find the argmax over all values theta of the sum over each data point of the probability of that point coming from the kth cluster times the log of the likelihood of the ith point given theta. So for example, before this was a Gaussian where we wanted to maximize this thing over the mean and the covariance, and we took the derivative and we found that we could do that in closed form, and I gave the equations on the previous algorithm. Now, depending on what this distribution is, we might need to run an algorithm to update to maximize this, or maybe we can take the derivatives and set to 0 and solve, but we'll have a different equation given the model that we're considering, given the densities, the likelihoods that we're using for the model we're considering.